introduce Jasna. So hi everyone, the speaker today is Jasna Urbančič, and the title of her talk is Optimizing Embedding Using Persistence.
Thank you, Sarah, for the introduction, and thank you for the opportunity to give a talk here. I'm going to be talking about my joint work with Primož Škraba on optimizing embedding using persistence. And first, I'll give you some background on how the embedding started, so how it came to be a thing. Then I'll give you some examples of how we do things and show you some results. And then in the end, I'm going to present some theoretical insights that we are trying to understand. So it all started with Florian Takens and his study of turbulence. He had an experiment. He had a cylinder he had two cylinders, and the space between was filled with fluid. And the inner cylinder was spinning with angular velocity. So this creates a turbulence and a chaotic attractor. So a chaotic dynamic system. And he wanted to study the attractor. So he knew that the shape of the attractor cannot be reconstructed from the spectrum. And he figured that it can be studied directly through the observable. And so he proved the following theorem. So if we have a manifold, a compact manifold of dimension m with a pair of maps, the first one is phi, it's a smooth diffeomorphism on the manifold, so it maps from the manifold to the manifold, and the other one is y, mapping from the manifold to real numbers, and that is a smooth function, and this is y represents our observable, and it's a generic property that the map capital phi mapping from the manifold to the higher dimensional space, it's defined here, that this is an embedding. And so one way to lift the time series to a higher dimensional space is to construct a time delay embedding. And we start with a delay vector with a d-dimensional delay vector. And this will give us a d+1 dimensional point cloud. Each of the components of the delays, we can imagine that it represents an axis in a higher dimensional space. So we construct the embedding by kind of constructing a point cloud. So first we take the unshifted signal. For the second component, we shift the signal for omega-1. The second component is, the third component is shifted for omega-2, and that gives us a point in a higher dimensional space. And some properties of the dynamical system are reflected in the shape of the embedding. What I mean by that is that if we have a periodic system, the embedding will be a circle. And if the embedding is kind of a high dimensional torus, we're dealing with a quasi-periodic process. A bouquet of circles represents recurrent behavior, and fractal geometry is linked to chaotic behavior. Next, I'd like to show you a video that shows how to construct, how one can imagine constructing the embedding. We take a signal and we copy it, we duplicate it, and we shift the copies, and then we can perform the sweep line, and this gives us an embedding. And if we choose a suboptimal delay, the embedding will be a thin ellipse. But if we choose an optimal embedding, so in this case, we're working with sine, and the optimal delay we know is half pi, we'll get a circle. And there is a very natural idea to connect the embedding to persistent homology. And persistent homology has been applied to the embedding, can be used to quantify periodicity. Many people have already studied that, and the theoretical side of the sliding window embedding is just slight, in a way, simplification of the time delay embedding, where our delay vector is something like that. So delay vector only depends on parameter tau, and the first component is tau, the second one is 2 tau, and so on, and the last one is d times tau. So a lot of work has been so far done with sliding window embedding, and the embeddings of functions have been studied on several types of manifold, and that includes Riemannian manifolds, including Möbius-Strip and Klein-Bottle. A lot of applications of sliding window embedding have been done on the real world signals, and those include Wiz detection, periodicity and gene expression, chatter detection and turning, and there's many more. So the first problem we are dealing with is we have discrete samples in practice, but we want to think about the system as continuous. And to overcome that, we convolve the samples with a Gaussian. And this gives us a continuous curve with very nice geometric properties, meaning the curve is C infinity. Alternatively, we can use another function to do a convolution. For example, sinc is an example of that, and sinc is very commonly used in signal processing. If one is inspired by deep learning, one can learn the kernel function and then do the convolution. And I'll explain what I mean by learning the kernel function when I show the example. So the main question now is, how can we find good embeddings? Takens's theorem only tells us that it is an embedding, but we don't have any quantitative control over the geometry of the embedding, which is very important when we're dealing with samples and finite data. And the answer to that is, well, we use continuous optimization of persistence diagrams. This has been recently applied to neural networks as a way to use persistence as a layer in deep neural networks. And we can think, when we are doing continuation of persistence diagrams, we can think about the points in persistence diagrams as pairs of positive and negative simplices. So here, one coordinate maps, so for one homology, one coordinate maps to the edge that creates a cycle, and the second coordinate maps to or is linked to the inside of the triangle that kills the cycle. Again, this is a very hot topic in applied topology, and many people are working on that. So I'm showing the video again because I want to show you, and I want to kind of that to sink in, that the embedding is very sensitive to parameters, which means that finding the right parameters that give a good embedding is very difficult. So to get from the embedding to a persistence diagram, we fix the parameters, we fix the embedding, and then build the filtration function on that. So we build the persistence diagram using a filtration function. And for the low dimensional settings, we use alpha shapes, whereas in higher dimensional settings, any distance-based filtration can be used, such as RIPS or Vietoris RIPS or check complex. So for a single recurrent behavior, we want to get from the thin triangle and a persistence diagram with kind of very low, so the cycle has very low persistence. We want to define a functional that will push that point higher up and make it more persistent. So we get a more equilateral or regular triangle with very high persistence. And so to do that, the functional looks something like that. So our goal is to have a single connected component. And this term will take care of that. So we want to minimize all the death times in zeroth homology, except for the infinite one, because we want to have one connected component. So for in the first homology, we want to have one loop. So we take the most persistent cycle, and we try to make the death as close to one as possible. And Y1, we are using signals. So our assumption is that the signal is has amplitude 1. So when we create embedding, we get the a circle with the radius 1. And finally, all other points in higher dimensions or so should be mapped to the diagonal. And for that, we have a noise term here, which minimizes the persistence of those points. And if we wanted to optimize a different recurrent pattern, we could adjust the functional. So to minimize the functional, we apply gradient descent. And this gets us from a thin ellipse to a circle. And just a technical side note, we are using MXNet, but most other kind of deep learning packages can handle computing the gradient and applying the chain rule to the functional. So if your setup is right, the gradients are computed automatically with one of the deep learning packages. Right, so now we assume we have a good embedding. And we are looking at circles and we want to reconstruct the signal from the embedding. And so what we can do is we can assign circular coordinates, and each co-cycle will give us one coordinate. But it turns out that the circular coordinate is not necessarily what our input was. So that's why we learn the local transformation for the points in the embedding based on the points in the embedding with similar circular coordinates. Right, so here's the exciting part. the results and the examples. First is sign, and we didn't do, so here we have no noise, just the plain sign function. And the green color is what we had in the beginning, and the yellow/whitish color is what we ended up with. And you can observe that we started with an ellipse, and in the end, we had something that looked very much like a circle. And as well, if we look at the persistence diagram, we started with this green dot as being the most persistent one cycle, and we ended up with the this white one here. The delays, or better, the kind of the Gaussians, the kernels, are shown in the picture here. And we can see how they shifted. And as a side note, we also optimize the sigma, so the width of the Gaussian, and that also changes. And if we were to estimate what the delay here is, it's here. So that's approximately half pi, which is what we stated in the beginning is the optimal delay for sine. And this also works if we apply some noise to it. So here we're working with noisy sine. The amplitude of the noise is approximately 0.1. And you see that here we had a very thin ellipse in the beginning. And we managed to increase it quite a bit in 50 iterations. If I left it on a bit longer, there's a chance it would look much, much, much better. And if you look at the persistence diagram, there is the green ellipse in the beginning was very much, had very low persistence, but with the optimization, we got it up to here. Here, I'd like to also say that if we're working with a very noisy signal and chose a bad starting delay, there might be some points here in the middle. And if there is no kind of persistent one cycle, the optimization doesn't work. Because if there is no one cycle here to increase, then the gradient descent fails. And here again, if we go back to delays, we can see that sigma kind of decreased, and it's centered between half pi and 2. So not too bad.
And Jasna, let me interrupt. So there's some questions. Michael, feel free to unmute yourself if you want to ask them. But the first question is, what's the noise model used here?
Oh, just random uniform noise added to it.
And then his second comment, or I guess question is, so the functional terms need, so the functional terms, you want to pick, well, sorry, I don't know how to parse this question. So maybe I'll let Michael ask it or type it again, but sorry, keep going.
So what I'm trying to ask in the question is, the terms in this functional here are all sort of representing something you're trying to in the optimization, right? So you have one functional that forces a connected component, one that forces one loop. And I'm asking whether the way that you build this functional requires you to pick a specific one cycle that you want to improve.
No. It will always choose the most persistent one at each step. So if we had 2 cycles, right. So it always chooses the most persistent cycle. That's the point. Because that's a technical detail, but we assume the persistence diagram is sorted first by dimension and then by persistence. so that the longest living structures come first. If that answers the question, I hope.
I think it might. Thank you.
Okay, we can discuss it after the talk.
Absolutely.
Right, so I've shown you sine, and one might argue, well, that surely doesn't work for other signals. Well, we tried it on sawtooth or triangular signal. And here, the main takeaway is that the embedding doesn't look like a circle. The embedding looks like a square. And while everything else kind of looks very similar, so persistence diagram, we improved the persistence of the most persistent point, and the delay is again kind of approximately at half pi. The embeddings look very differently based on the shape of the signal. And a very similar thing happens when we have some noise added to the signal. So another problem we might run into is, what if the dimension of the embedding is too low? So here I have a periodic signal, and that is sine plus sine of t plus sine of half t. And it is periodic, but we see that if we embed it into 2 dimensions, it's self-intersecting. And in that case, the gradient descent cannot improve the embedding because just the whole setup is not appropriate. And something in a way similar is embedding into too high dimension. So here, the first picture is the functional when we're embedding the sine into 2 dimensions, and we have delay 1 and delay 2, and the colors, the heat map shows you the values of the functional, and the black dots show you where the gradient descent converges after 50 iterations. And the black dots kind of form the figure 8 here. And it turns out that when we compare the embedding at two of those points, we get something similar, but it kind of looks rotated. So we started with an assumption that cosine, sine, and sine is the optimal embedding of cosine into 3-dimensional space. And under the hypothesis that what we see is a rotation, cosine, sine plus sine of t of epsilon, and sine of t plus minus epsilon still represents a good embedding for small epsilon. And if that is a rotation, then we have kind of a relation between those two. And we can write it out like this. And assuming this is a rotation, R represents a rotation matrix. And if we write it out, we can see that firstly, R doesn't reserve the norm. And secondly, if we compute the eigenvalues, R is not a rotation matrix. So this is not a rotation. And further, while those things look like circles, they're actually planar ellipses, which means that embedding in the dimension too high might spoil the geometry a bit. Right, so I hinted in the beginning that we can learn the kernel function. So far, when we were convolving with Gaussian, our parameters or variables in the model were delays on one hand, and sigmas, which are the width of the Gaussians on the other hand. But here, what if we want to learn the function that will give us if we convolve the signal with that function, will give us a circle. So our parameters or variables in the model are the function values. And we did that. And here are the results. So again, we took sine. There is no noise added to it. And we start, so we didn't bother with scaling at first. So we start with the embedding like this. If I were to zoom in a lot, you'd see that it's still a circle or something kind of topologically equivalent to a circle. And when we apply gradient descent, it turns into an actual circle. And the most fascinating bit here is how the kernel functions look like. So we can see that one of them, so this one, looks very much like a sine. And the second one seems like it's shifted for half pi or quarter of the phase of the period. So yeah. So we tried that in 3D as well. Then we tried that on another signal as well, on the triangular signal. And the interesting bit here is that the embedding, which was previously a square, is now a circle. And compared to the sine before, the kernel functions now look like a mess, but the embedding is a circle, has a geometry of a circle. Again, here we also did just 50 iterations. So if we let it go on longer, things would look better. So we conjecture here that the space of those functions that we use for convolution could be very interesting. So we did the similar thing in 3D, and the results are not as surprising, except now we have 3 kernel functions, and one of them looks like a cosine, whereas the other 2 look like slightly shifted sines. And for sawtooth in 3D, again, the kernel functions look like a mess, but the embedding has the properties that we'd like. So this kind of leads me towards the more theoretical part of the work. So we know that the gradient descent will give us some minimum of the functional, but are there any guarantees? So we came up with a conjecture, and it's stated here. So let X be a closed, non-intersecting piecewise linear curve in 2D or 4D, but definitely not 3D, because in 3D we get knots. So under the following persistent gradient flow, the PL curve converges to a circle. And the gradient flow maximizes the persistence of one cycle and minimizes everything else. So the setup here goes kind of like that. So we are working with 2D case for now, and we split it into convex and non-convex case. So to start up with convex case, everything in white, so the PL curve with its vertices and edges is born at time 0 because we add in everything at the same time. So the persistence of the curve is determined by the last one cycle that gets filled. So in a way, we have a single critical point, and that is the center of the circumcircle of the last inside of the triangle that gets filled. And our goal is to maximize the persistence of the PL curve. And to do that, we maximize the depth. So to maximize the depth, we move the vertices away from the critical point. So we move those 3 vertices, which determine the triangle, away from the center of the circumcircle. And we are looking, so in the process, we are looking for the ratio of the circumcircle of the last triangle that is added, and the minimum bounding ball of the PL curve. And when the gradient descent is done, and if the curve converges to a circle, then those two will actually be the same. So the radii will be the same. So the ratio converges to 1. And we move the points away from the center of the circumcircle for lambda, which is the step size of the gradient, and then the gradient of the distance between the point and the center of the circumcircle. And because those points are all the same distance away from the critical point, they all move the same, and we call that move, like, we named it X. And in the worst case, where all the 3 points are at the same time on the bounding ball, and well, when at least one of the points is on the bounding ball, as well as, well, when one of those 3 points is on the bounding ball, that's our worst case, because then the bounding ball also increases. And we can see here that, so in the computation here, that that the ratio will always improve, and when it doesn't improve, the radii are equal. Right, so moving on the non-convex setting. Again, everything in white has been born at time 0. And we are looking to maximize the most persistent one cycle and minimize everything else. But here we don't only have 1 critical point, but in this case, we have 3 critical points, and we need to understand their pairing. And the critical points are the red edge, which is the one that gives birth to one of the cycles, to the extra cycles we get. And then we have 2 triangles, one that kills the larger cycle and one that kills the smaller cycle. So, and to understand that, we need to understand we want to kind of understand the combinatorial pairing, how the combinatorial pairing of the of those critical points evolves with gradient descent. And we think that the argument we are trying to come up with, or the argument we are working on, covers not only 2 dimensions, but works in higher dimensions as well. So in this talk, I presented the embedding spaces and optimization of time delay embeddings on for time series data. And the work on that is exciting. Well, it excites me because it offers a more automatic way to approach embeddings and to understand geometry and topology of embeddings. On top of that, it makes topological data analysis easier. There are still quite a few open questions, though. One of them is the further study of the reconstruction of the input signal from the embedding. So the one that's based on local reconstruction. We still have many questions on that that we don't know how to answer. The other one is better theoretical understanding of the gradient flow, optimization, and embedding space. And this is in a large part linked to the gradient flow on a PL curve. It would be great to understand how the combinatorial pairings between those critical simplices or critical points in the space work. So in our functional, we only kind of deal with global topology. We count loops. We want to increase loops. So it would be interesting to explore the trade-off between local and global topology. And lastly, we would like to apply our approach to real world data. So you see, we only used toy examples and synthetic signals. So trying it out on a real problem on a real signal would be great, and would give us some further insight into how topological data analysis and analysis of the embeddings can aid the understanding of time series data. And with that, I conclude my talk and thank you for attention.
Thank you. So maybe before we take questions, I would ask everyone to unmute themselves and clap. Okay, so now it's time for questions.
So given the future work list you had, is there any particular real world data you're looking at approaching, or that you're particularly interested in?
So we might start working with some data on from smart factories or something similar very soon, but we don't really have any concrete, very concrete things we'd like to either work on or show. Just in general, we are working on, like, we would like to work towards seeing how this works on real world data. So yeah.
All right.
I have a question. So when you optimize to flow towards this circle, that circle sort of like an input, you sort of decide, like you're asking how periodic is this system, but you might do a similar thing with a torus if you think there's, for example, quasi-periodicity, things like that. Is that correct?
Yeah, so here in the functional, if I knew there were, for example, 2 circles or so, I could adjust the term here, or even if I knew that the process is quasi-periodic, I can kind of adjust the functional to respect the Betti numbers of the torus. And a lot of this can actually be done automatically when we're defining, well, when we're doing the setup in the code.
Okay, more questions.
I have a question. So if I'm looking what you are doing, it seems to me that, okay, so if you know that there is a periodic orbit, you know how to put it into the coordinates where you see it the best. If you know that there is maybe something quasi-periodic, you know how to do it again. But what do you do if you just have data and you don't know what is in the data? Let's say there is a chaotic system which has a lot of unstable periodic orbits. Can you somehow use this to identify those orbits?
So one idea we had previously, and we haven't managed to follow through yet, is to see if this can be made incremental in a way, so that we first look for one periodic behavior and then subtract that from the input signal, and then work on that kind of reduced signal and try finding kind of other smaller recurrent patterns. And an example for that would be if you imagine the traffic data where you have yearly, weekly, seasonal effects, and on top of that you have the daily cycle. If the approach, the incremental approach works, you could be able, well, you would be able to take out each specific recurrent process.
Okay, but so what I'm thinking, so on one of your slides, when you have these two different circles, which you have to distinguish which one is the right towards the end, right? So if I imagine, there could be different types of.
I'm sorry, this one
very end when you were doing the optimization of the.
Oh, the PL curve.
Yes, after that, even this one. So right here, you can have different types of dynamics. You could be really going around the whole thing, or there could be maybe a homoclinic point somewhere in between, and you could have two different circles. Okay,
so the setting here is that everything in white is added at the same time. So the edge in red is not added at the same time as the edges in the white. So in this case, if that was an attractor, it would go around like that. So and then continuously.
But how do you know that this couldn't be sampled from a system which actually has a homoclinic orbit somewhere around that birth line, and these are two periodic orbits on the sides?
I'm not sure I follow.
So I understand. I agree with you that if everything goes around, then you have one periodic orbit. But imagine that you had two periodic orbits which would be kind of meeting in the middle.
Oh, okay. So like Lorentz attractor.
Exactly.
Okay. Yeah. So we did try a bit with the Lorentz attractor, but we haven't managed to put the work on it concretely. But the idea there is, at least for us, is when we have a system with kind of two orbits, to observe the transitions. So the interesting bit here is that where the transitions from right orbit to left orbit and from left orbit to right orbit happen. So it would be, we are working on kind of finding the optimization for that. But here, I think the most important bit is to get the number of orbits that are in the system right. And then we can observe the transitions between the two orbits.
Okay, thank you.
I hope that answers your question.
One follow-up question on pretty much what you just said. Do you have any thoughts on how to detect an appropriate number of orbits to aim for? Since that seems to influence your choice of functional quite severely, it seems like you would need to know quite a lot about the system you're studying in order to pick an appropriate functional to optimize. What are your thoughts on how to figure that out from our raw data pile?
Yeah, so to avoid that, our kind of idea or wishful thinking, or however you want to put it, is to have that kind of iterative approach where you first find one recurrent behavior and then reconstruct it and subtract it. And then you find the second one and the third one. And in that way, you would be able to get the number of behaviors without having to know the dynamic in advance. But without knowing the dynamic in advance, I agree it's very difficult and the functional needs to be adjusted. So I think now the current state is that we are basically guessing. However, in the future, we'd like to have something more automatic for the detection, though we are not yet fully sure. We don't know yet how to do it.
Thank you.
Okay, any more questions?
Hi, I have a couple of questions, Janice. If you can, please go back to your functional.
Yes.
Maybe, yeah, there. Thank you. Maybe I missed something here. So if you want to add if you want to modify your functional to actually add or consider higher dimensional features, where do you need to modify it? What do you need to do?
So let's say we are adding another recurrent pattern so that we have 2 loops. In that case, so we say, so in a case for a single recurrent behavior we have here is we are only looking at k equals 1 and mk, so the number of loops in dimension 1 that we're looking for is 1, and all the other all the higher dimensional features are set, so the number of them is set to 0. And now if I try and change the color, right, I'm using blue now. So we have 2 loops. We are looking for two loops, which means two one-dimensional, so 2 one-dimensional features. So m1 will be equal to 2 and the sum will go up to 2. And that's what that means, is that we are looking for, we are not only optimizing the one most persistent cycle, but we're optimizing the first and second most persistent cycle.
Okay, got it. So what about voids? I mean, you have connected components, loop, and voids.
Yeah, so for that, so K here counts homology group. So in this case, we have for loops, we have K equals 1. For K equals 2, we have, so if we were doing a Tori, we would have M2 equals 1, and this counts voids. And in that case, that sum will kind of split into 2. So this one will cover K equals 1, and then we have another one that covers K equals 2, and we'll have for E in diagram 2, and we'll start with I equals 1, and we'll go to I equals 1, so M2 equals 1. And assuming that we want the void to also have kind of volume or persistence of 1, we'll do 1 minus depth of that void.
Oh, I see. I see. I have some other question related with this function. So your goal is to optimize your functional. So here you actually are considering you are using gradient descent. So that's good, and that's good because, well, that's good. That's okay when you actually have a one global optimum of the function and so on, because you don't get, I mean, you don't worry about many local optimums or something like that. But do you always have a global optimum on the function that you want to optimize? I mean, those actually could happen that your functional could have multiple optimums.
Yes. So if I show you, even the case we are working on now actually has more optimums. So if I were to do the same plot of the functional with delays going from 0 to 10, so here I'm just going from 0 to pi, and if I went from 0 to 10, which is kind of 3 pi, I would get the 9 of the same pictures. So I would get the functional here with the delay is periodic, just as the system is periodic. So this one is this one here, and it would be repeated nine times to kind of form tiling in a way. If you know where I'm going at. So because the system is periodic with, let's say, period, so I'll go back to the functional. So it's periodic with some period, let's say, I'll use lambda here, although I used it for something else before, but okay. So I have a signal that has a period lambda. So what that means is that functional will be, and if I have a delay omega 1, then if that is optimal, if I take omega 2 times omega 1 optimal, I will have the same value of the functional as I had here.
Okay.
So the functional itself is periodic.
Yeah, got it. Thank you. It's very, very interesting research. It would be really great to see results using real data, applied on real data. That would be very interesting. Thank you so much.
Thank you.
I have one more question on the functional, if I may.
Yes.
It looks on the setup, and when I'm trying to inspect the terms of the functional, like you're trying to force your loop to die at time 1 specifically. But doesn't that change if the amplitude of your time series changes?
Yes, it does. So one assumption we make, and I forgot to mention in when I was explaining the convolution, is that we assume our signal has amplitude of 1. We did that to kind of avoid any explosions or anything, because if we were just to increase the death time, in a lot of cases, that would mean that just it has happened that our embedding got way larger than it should based on the signal. So this is kind of the regularization or normalization term as well. We are assuming the signal has amplitude 1, so that the circle has diameter 1. But of course, we can either work on changing that, or we can always use a scaled signal.
All right, thank you very much. It's been a great talk.
Thank you.
Okay, thank you. So I'm going to stop the recording now and free to ask more questions after I do that. But thanks again, Jasna, for the wonderful talk.